All right, so if we're taking the derivative of this volume formula with respect to time, what's the left-hand side going to look like? Yeah, dv dt. All right, dv dt. And then, what do we have to do with the right-hand side?
Find the derivative.
How?
Is it product rule?
It is the product rule, okay? We got a pi over 3r squared times an h. All right, so we got to do the product rule. Okay. So what'd you guys get?
2 pi over 3 r dr dt.
Okay, so that's the derivative of the first part times, good, h, Arthur, times the second part.
And then plus dh dt.
Okay, dh dt
And then just pi over 3 r squared.
times, good, the pi over 3 r squared. Okay? So here we're using the product rule, and when we use that product rule, every time we're taking the derivative of something that's not the variable that we're taking the derivative with respect to, we've got to use that chain rule and multiply by the derivative of that implicit function with respect to time. So r is an implicit function, so it's times dr dt. Okay, same thing with the h and the v. Okay? Now, this transitions us into what we're looking at in this lesson today and on Wednesday, and that is related rates, okay? We know that the derivative gives us a rate of change, but in this case, there's 3 different variables, and all of them have a different rate, okay? Here's kind of a time-lapse picture of this water draining out of this, and you can see here, when this is full, let me get a better color here. When our cone is full, the radius is this and the height is this, okay? But when it's down here, the radius is smaller and the height is also smaller. Then we get down here and the radius is smaller still and the height is smaller still. So obviously, the radius is shrinking. There's a rate of change. The depth of the water, or in this case the height as it's called, is shrinking. And also the volume of water that's in the cone is shrinking. Okay? Now, I'm actually want to answer this second question down here first. Does the rate of change in volume depend on the values of r and h?
Doesn't the rate of change in volume affect R and H?
It depends on your perspective, but yeah.
Well, if the volume's going down, isn't R and H going down too?
Okay, yeah. As the volume decreases, r decreases, h decreases. They're all decreasing together. To calculate the change in volume, it is going to be dependent, though, on R and H, like you guys are saying. Now, I want you guys to think practically here, okay? How will the change in volume be affected by how deep the water is? In other words, what H is.
Like directly proportional? Is that what you're like asking?
Not even that formal. Just if I have a deeper amount of water, what's that going to do to how fast the water is flowing out the bottom? It's going to go faster, okay? Yeah, it's going to go faster because you have more weight, right, pushing it out the hole. If we were just tossing water out the window, it wouldn't matter if it were a cup of water or a gallon of water. It's going to be the same, it's going to fall at the same rate. But here we're shoving it through this small hole at the bottom of the funnel, if we've got a bunch of water up top with more weight pushing it through, it's going to push it through faster than, say, when it's only half full and there's less weight pushing it through that hole. Okay? That's why, you know, the water pours out and then it goes to a trickle as there's just a little bit left, you know? Because it doesn't have that force behind it pushing it out. So yeah, it's going to affect it, but also, here's where we can look at our equation that we just came up with up here. What is dV dt?
The rate at which it drains.
I'm sorry, what?
Volume and time.
Okay, what about volume and time? It's volume over time, so that is the volume change, the rate of change in volume over time. Okay, so this is our rate of change in volume. Okay, in other words, in this case, how fast is the water pouring out the bottom? Okay. What about these others? What's dr dt? Okay, yeah, it's the rate of change of the radius. Okay, we could say it's how fast the radius is changing. And dH dt? Okay, we're picking up on it here. How fast the height is changing. Okay? How fast the height is changing. So, as we look at a problem like this one, let's look at the kinds of information that we would be given. Alright? So here, it says that our height is changing at a rate of negative 0.2 feet per minute. Okay? Or negative 0.2 of a foot per minute. Alright, so what does that represent?
DRDT.
Yeah, that is, wait,
Oh no,
what is it?
DH. I thought that was it.
Yeah, dH dt. Okay, so that's our dH dt. And that says the radius is changing at a rate of negative 0.1 of a foot per minute. What is that?
That's DRDT.
That's our dr dt. Okay? dr dt. So, how would I find the rate of change in volume when the radius is a foot and the height is 2 feet? Plug it in. Yeah, come on guys. We just plug it in. We've got an equation already, right? We want to find, we're trying to find the rate of change in the volume. What is that?
DVDT.
Yeah, we're trying to find dV dt. Okay, so that's there. We know the rate, we know the dr dt, we know the height, we know the dH dt. All we've got to do now is plug them in. Okay, and this will tell us how fast the water is pouring out the bottom at that moment. Okay, so let's do that.
If you go to do that and you have too many unknowns or not enough unknowns, chances are you took the derivative incorrectly. So go back and check your derivative. And don't plug in, like you're saying, find the dV dt when the radius is 1 foot and the height is 2 feet. You don't want to plug in those values until after you've taken the derivative, because it's going to throw your whole equation off.
Yeah, because when you differentiate, you want them to be variables. If you plug a specific number in, then they're constants, and that's going to mess everything up. Okay.
Have
Thank you.
fun, related rates.
I'm really one for you.
All right. Oh, thank you.
Do you want me to pick up a bag for you? 'Cause I'm-
So what'd you guys get?
Oh, I didn't.
Oh, come on. You're letting me down.
You're gonna candy.
Plug it in here. 2 pi over 3 times the radius times dr dt times the height plus pi over 3 times the radius squared times dh dt. Okay, so we get negative 0.2 pi, and typically AP doesn't care about units of measure. All right, in fact, unless they ask for them, don't bother putting them down. Okay, now that's AP. For our class, I would like you to use proper units of measure to show me your understanding, okay? This isn't that difficult. We're talking about a rate of change for volume. So all you have to think about here is, what is our unit of measure for volume? In this case,
dv dt cube. Feet.
No.
feet are our units of measure, so in volume we'd be talking about cubic feet, okay? So cubic feet per, what's our unit of time?
Seconds.
Minutes.
Minutes, okay? So cubic feet per minute. That's how fast the water is coming out of this cone at that moment. Okay? Yes?
So all you did was like where it said, when we said negative 0.2 feet per minute was dh dt, we just plugged in negative 0.2?
Yeah.
That's it?
Mm-hmm.
Oh.
Yeah.
I can do that. Thanks.
That's why, guys, identifying, when you read a problem, identifying what these are in terms of the dh dt, dv dt, dr dt, that's really the most, sometimes the most challenging part of the whole problem, but that's the most critical part of the whole problem, because that tells you where to plug things in, okay? Finding the derivative really isn't that hard at this point, okay? And obviously evaluating it isn't that hard, but getting stuff plugged in the right place can be the challenge, all right? So let's try another one of these. We've dropped a pebble into a pond, and it causes ripples in the water. So the pebble hit right here, and it's causing these ripples. And the outermost ripple, we have this radius, okay? And we've got the outermost ripple going around here off the picture, and then something like this. There we go. Okay? So there we have this circular ripple going out in the pond. And this may seem silly, but you could do the same thing if you were talking about the shock wave from a bomb dropping, or earthquake happening, or the spread of a disease from wherever it originated, or even the police setting out a perimeter trying to capture someone who's running away, you know. What we're going to find here is the rate of change in area. At what rate is the total area of the disturbed water changing? We could then expand that to any of those other applications. What's the rate of change in how many people are infected, or the shock wave of the bomb is growing at, or from however long the suspect started to run away, how big of a circle and how much more area is it the more we delay. Any of those things, though, that we could then use this to this same concept to work with, okay? But we'll just deal with a nice calm pond for our example, okay? It says that the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. What is that in light of what we're doing? Yeah, that's going to be a dr dt. The radius is changing at a constant rate of 1 foot per second. Okay, that's dr dt. When the radius is 4, so r equals 4 feet, at what rate is the total area of the disturbed water changing? All right, so this is what they're asking us to find. How would we express that?
dA.
dA dt. Okay? dA dt. So, before we can differentiate, we need an equation, though. Thinking about this situation here, what would be an appropriate equation to use that we could then differentiate to find dA dt and have dr dt in there and so forth?
Area of the circle.
All right, yeah, we're talking about this circular ring, okay? So we're going to use the area of a circle. Area equals pi r squared. Okay? Pi r squared. Now, so we take the derivative. What's the derivative of the left? dA dt. Okay? dA dt. That's what we're looking for anyways. That's kind of nice. And how about the right-hand side?
2 pi r dr dt.
There we go. 2 pi r dr dt. Okay? Now we just plug it in. All right? We take this constant rate of 1 foot. We plug that in for dr dt. We plug 4 in for the radius. And we get 2 pi times 4 times 1, so 8 pi. And then what would our unit of measure be?
Feet.
Okay, that's our unit of measure for area. This is the rate of change of the area. So it's square feet per second. Okay? Square feet per second. So that's how fast the area that this thing is covering or impacting is growing at that moment. Okay? Any questions? Okay.